All right, so what we're going to do here is we're going to do another related rate, and we've been struggling with these colon problems, so I thought we'd do one of these. And this one says water is leaking out of an inverted tank. That means it's like a little water cup. All right, so
Why did it have to say inverted?
Because a cone that's not inverted looks like this, like a dunce hat. All right. So what it says here, guys, is you have a cone that water is leaking out of at 10,000 centimeters per minute, and I show that at the bottom of my cone, which is in red. And at the same time, water is being pumped into the tank at a constant rate, which is up here, water pouring in the blue. The tank has a height of 6 meters, a diameter of 4. I mark those in green. And it says if the water level is rising at a rate of 20 centimeters per minute when the height of the water is 2 meters, find the rate at which the water is being pumped in. So they want the question mark here, guys, the blue question mark going in. And what they told you were these two facts, or this fact. They want the rate of the water going in, dV dt in, and they told you that the change in the height with respect to time when h was 2 meters was 20 centimeters per minute. So at that instant, it's changing by 20 centimeters per minute. All right. We have to know some stuff about this colon situation, all right? And if I blow this down, first of all, we got to know that the formula is what? 1/3 pi r squared h, 1/3 area of the base times the height. Base is a circle, all right? And we have to know one other big fact about dV dt this time. It's just not water going in. It's water going in and out, right, guys? So when we find dV dt, does everybody agree it's in minus out? There's pumping water in, there's water leaking out. Not a big deal, but we're going to realize this fact for the end and deal with it, okay? Because they just want in, and I'm going to find dV dt for the situation. All right. The big problem I see with you guys is you cannot, listen, if you take the derivative of this right now, I want to be clear that this is a product rule. It's r squared times h. All right? And if you take the derivative right now, and you can if you know all the variables. I'll take respect to r first. You get r squared is 2r. Yes. We're trying to find the volume coming in.
Okay.
All right? And if I want to take the derivative with respect to time, well, I can. And if I do it with r and then h, and you guys should see how this happened. All right? You should be able to follow this. We don't want to really do this. This is the derivative of this with respect to r. That's why it's dr dt. This is the derivative with respect to h of this, which is why it's dh dt. But the problem with that big green equation is I only know dh dt. I don't know dv dt, and I don't know dr dt. Those two are unknown. So this green equation is useless usually for us, all right? But we have principles always built into tanks. And this situation is we know that we have a set of similar triangles buried in here. I have the triangle that is 2 by 6, okay? And you can use numbers for that. And I'm going to drop the meters because the meters are going to cancel. But what I see you guys doing, if I grab another triangle here, and it said 2, you can't put 2 and r here. You need the r, but guys, what you need to realize is what you're setting up on the blue triangle is what is changing. And it has to be in terms of variables. And if the variable can change, you can't use a number. So my other triangle in this case is r and h. So now I can set up a ratio, because as the radius changes, the height changes, and as the height changes, the radius changes, right? We should be able to picture that. As it fills, the circle gets bigger. I cross multiply, and I get 6r equals 2h. I realize up here I have dh dt, so I really are going to want to get rid of r. So I solve for r, and I get r is 1/3 h. All right? I knew this, and this is what kills you guys. I know you're looking for procedures. There aren't procedures. you think about what the derivative here was, and you knew you couldn't handle dr dt. So you make a way to get rid of it, all right? Comes with cracks and lots of types of problems. So I got to take, now I'm going to just say, well, okay, I can take my 1/3 h for r and plug that in. Volume equals 1/3 pi, 1/3 h, quantity squared h. I get volume equals, third h is 1/9 h squared, so I get 1/27 pi, because the third times the ninth, h squared times h is h cubed. And this equation does not stay the same. It's based on the height and the diameter. If I change the tank dimensions, this formula changes. Can't memorize this. A couple people just wrote down, I think, the one we used a couple weeks ago in class. Not the same. All right? Now, this, if I take the derivative of this, I end up with something I like. dv dt, because it's respect to time. The derivative of h cubed is 3h squared. So I'll write 3/27 right now so we see that. I'm going to change that to 1/9 here in about 2 seconds. But I get there. And all of a sudden, I say, oh, those are all variables I know. And if I just shrink the screen down a little bit, think about it. I know h. I know dh dt, right? I need dv dt, so I can do this, all right? So I'm going to plug in those numbers and get a solution. So I get dv dt equals 1/9 pi. H was 2 meters squared. dh dt was, oh, I love these book problems. Does anybody see the problem I have? I have 20 centimeters per minute, and I have 2 meters. It gave the volume here in centimeters cubed per minute. So what I'm going to do before I even square it, is I'm going to erase the 2 meters. I'm going to change it to 200 centimeters. All right. So now I'm going to do some math. I got to grab my calculator. And I'm going to treat pi like 3.14. I'm going to have some rounding error. So I'm going to take my 1/9 times 3.14 times 200 times 200 times 20. And I'm going to get that the answer here is 279,111 cubic centimeters per minute. I could leave this in terms of pi, but I'm not going to. But that's not the answer this time, guys. That's dv dt. And if I blow the screen back, remember from the get-go, we just found this. We found what's happening overall, right? But remember from the beginning of the problem, we had some water pumping in and we had some water flowing out. They want how much they were pumping in. I just found dv dt. They want dv dt in. Kind of hard to follow. This is a more complicated problem. All right? So what I'll do then is I know that the net is 279,000. All right? So I got 279,1100 centimeters cubed per minute. That's dv dt. I don't know dv dt in. That's what I want to know. But I know the out's 10,000, right? Cubic centimeters per minute. So it's leaking a little bit, and it's pumping in a lot. So to get a net of 279, you add the 10,000 over. The final answer is 289,111 cubic centimeters per minute. I suppose, and again, I always talk about this, the hardest parts usually are right in here, right? You have to always get to one variable. All right?
For like that step right there, since you have the h equals 2, would you be able to find what the radius is there and plug that in instead of having 1/3 h?
Nope. Because remember, the whole idea is if something changes with respect to time, you got to have the derivative. So you can't be plugging numbers in till the bitter end after the derivative is done. You have to do the derivative in terms of the variables.